So if we're looking to do a 99% confidence interval, we're going to start by going to number 2. It's going to be, instead of distribution this time, it's going to be interval. And we're only ever going to be doing Z intervals because we're only dealing with the normal distribution. And it's a sample, it's a 1 sample. And here we're going to set our confidence level, instead of to 95, it's going to be 99. Our standard deviation of our distribution, if I just jump back, is going to be 35.2. Our sample mean was 68.89. And our sample size, I'm pretty sure, was 20. I'll just double check that. Yep, so 20. And then if I go through and find my confidence interval, I get 48.6 up to 89.2. So 48.6. So for 99%, 48.6 is less than or equal to mu, which is less than or equal to, anybody got the upper value there? Yep, 89.2. Okay, all right. Now, reminding you of a couple of things I mentioned last time. Make sure that the middle symbol in here is mu, not x bar. This is, we are not finding an interval on x bar, on our sample mean. We know what that is. That's 68.89. We don't even want an interval on that. It tells us nothing. The interval is always for the population mean, which is represented by mu. Do you have it representing sigma for some reason, or mu, not mu, or x bar, you will lose a mark in the test and the exam. It is critical that you actually understand what this is telling you. Therefore, it's critical that you give the right symbols. Because remember, when I come to mark it, I mark what I see, I don't mark what I think you know. If I marked what I think you know, you'd probably all get 100%. Okay, right, let's move on. So, a company produces marbles. As a result of the process used, the weight of the marbles can be modelled by normal distribution with a standard deviation of 1.1 grams. The mean weight of the marbles is unknown. To investigate the mean weight of the marbles, the company randomly selects marbles and weighs them. Each sample taken contains 100 marbles. Okay, so we've got a sample size. So let's just identify key information. So we're going to need the standard deviation, that's 1.1. This 100 marbles is going to be the value of n. That's my sample size. And now I've got a mean weight of 5.72 grams. Find a 95% confidence interval for mu, the mean weight of the marbles based on this sample. Okay, all right, we come back to here. They want us to find a 95% sample. So I'm going to change this 95 to 99, or rather the other way around, 99 to 95. Sigma was 1.1. The mean was 5.72. And the sample size was 100. So it goes between 5.50 and 5.94. Notice here I'm rounding correctly because we've got a 5 after there, I've got to round up. So 50 to 93. This comes from a past exam. Notice that it's worth 2 marks. What's your 2 marks for? Well, 1 mark for the bound. The other mark, I've already mentioned it, rounding this mu in here. There is no, generally in most cases, there will be no marks actually awarded for working it out longhand. No marks are actually substituting into the formula, or no extra marks. two confidence intervals based on sample 2 and sample 3, so they did another 2 samples, are drawn on the diagram below. So they're shown here. Sample 1 goes, which is what we've got to draw, goes from 5.50, so from here, up to 5.93. So that's 5.6789, so it would be about here. So that's 5.5 up to 5.93. So that's our confidence interval drawn on the diagram. Then it says, is it possible for mu, the mean weight of the marbles, to lie within all three confidence intervals? Give a reason for your answer. Well, if it's in this confidence interval, remember mu can be anywhere in this confidence interval. It can even be right down the end, right on the end. The endpoints are considered as part of our interval. So it could be there, or it could be there, or anywhere in between. Now, if it's somewhere here, it will be also in sample 3. If the mean is at 5.5, it will both be in the confidence interval for sample 1 and 3. And if it's up around this region, well, it will be in the confidence interval for 1 and 2. But there's a particular value or set of values where if it's in this region, yes, it's going to be in 1, but it's not going to be in 2 and 3. You see, 2 and 3 don't overlap. And so therefore it's possible for it to be in sample 2 but not in sample 3. And it's also possible for it to be in sample 3 but not in 2 because there's no overlap or there's a region in between those two. So let's write that up. Because the confidence interval, which I'm going to shorthand to CI, confidence intervals from samples 2 and 3 do not overlap. It is possible for mu to be in one interval but not the other. In fact, if mu is in interval for sample 2, will not be in the interval for sample 3, and vice versa. Therefore, not possible. See, I don't really have to talk about the interval from sample 1. The critical fact is that sample 2 and sample 3 intervals don't overlap. Therefore, if it's in one, it won't be in the other. It can't be in the other because there's no common region. Notice I also make a nice, clear, definite answer here. Okay, I actually answer the question here that it's not possible. So it's good to give you reasons, but it's also important to actually state that it's not possible. Because that's what I asked. Okay, all right. After further investigation, it's determined that the mean weight is 5.73. Does this mean that there was a flaw in the way in which sample 2 was taken? Give a reason for your answer. Well, remember we're only finding 95% confidence intervals, so we're only 95% confident that it contains the mean. So no, it doesn't mean there was a flaw in the way sample 2 was taken. So 95% confidence interval means we are only 95% confident it contains population mean. Therefore, it is possible for interval not to contain mu and sample 2 was one such case. Hence, does not mean there was a flaw in sample 2. I misread the question. Okay. You're saying that includes 5.73? Yes, what I did is I sized down the diagram, and I reckon I don't size down the bars. So interval is 5.736, 7, yeah, that definitely contains it. So probably sample 2 should look something more like that. I think that works better. And actually sample 3 should be extended a little bit. Yep. So it was when I rearranged the diagram that it kind of went out of whack. Thanks for pointing that out there, because that's important. Consumer group is interested in a comparison of 2 different brands of AA battery. For one brand, AA battery, the cost of a single battery is 0.99. Running time has a mean of 8.1 hours and a standard deviation of 0.25 hours. That's probably going to be useful information. Okay, for a cheaper brand, the cost of a single battery is 90 cents. Test is conducted to compare the running times of budget batteries and alpha batteries. So alpha batteries has the mean of 8.1 and 0.25, and that costs 99 cents, and a cheaper brand, which is the budget one, costs 90 cents. Sample of 10 budget batteries is randomly selected, and the length of time for which each battery operates the same specific electronic device is recorded. So the running times of the budget batteries are shown below. Find the sample mean. How do we find the mean of 10 values? Yeah, what do we do on the calculator? What's the easiest way of finding the mean? Yep. It's even easier. We just add them up and divide by 10. Okay, let's find the mean. We go. Add them up, divide by 10. Right, what do you get? 7.98. Okay. All right, and that is in hours. Now, the running time of budget batteries is normally distributed with a mean of mu, a standard deviation of another 0.25 hours. Construct a 95% confidence interval for mu of B. Okay, let's go to our calculators. Okay, confidence level is still 95. Standard deviation is 0.25. The mean was 7.98. And the sample was 10. The sample size was 10. So, putting those values in, if I go through and calculate it, I'm going to get 7.83 up to 8.13. So, 7.83 is less than or equal to mu, which is less than or equal to 8.13. Okay, alright, that's our 95% confidence interval. We're 95% sure population mean is in there. So, the mean running time of mu of A of alpha batteries is shown on the number line, so it's there. Because remember we were told that mu is 8.1 hours, so 8.1 is being shown there. On the number line, draw the confidence interval for mu B that you found in part AII. Okay, so what was it? 7.83 up to 8.13. So 7.83 would be about there, up to 8.13 is about there. So that's the confidence interval for B. So ask, what can we conclude from your confidence interval about the mean running time of budget batteries compared with alpha batteries? Give a reason for your answer. Well, if we look at this confidence interval for the mean, it could be higher than 8.1. It could be as high as 8.13. In fact, budget batteries could actually last longer than alpha batteries. Or the mean could be as low as 7.83. In fact, it could be a lot less than budget batteries. So what can we conclude? We cannot conclude. We don't know. So what we say is the mean running time of budget batteries could be greater than alpha batteries 8.13 hours, or less at 7.83 hours. Hence, we cannot tell if budget batteries last longer or not. We can't tell. This is the most indecisive. Well, in this part of the course, it is good to be indecisive and unable to make definite conclusions. It's the most indecisive you'll ever be in maths. We can't tell. We don't know. Because it could be that they last longer, or they may not. Okay, what is the maximum level of confidence with which will enable you to make a definite claim about the mean? Well, there's probably two key things coming here, but we would be able to make a claim about the mean if it ended at 8.1 or just below. So if our n value was 8.1, we would be able to make a claim. So we need to use that idea to find the maximum level of confidence. So let's remind ourselves that x bar plus k times sigma on the square root of n is the upper bound. And we can say that if it equals 8.1, we can make a claim. Because you see, if the upper bound is 8.1, then we can definitely say that the mean isn't equal to the mean of alpha batteries. And so then we can say that alpha batteries last longer. So x bar was 7.89. So 7.89 plus k times 0.25 on the square root of n is going to equal 8.1. So if we then solve this, it's going to be k times 0.25 on the square root of n is 8.1. Take 7.89. And we're going to be multiplying by the square root of 10. Possibly what we should say is, because the upper bound gets included, we want it to be less than 8.1. Because as long as it's not 8.1, we're going to be sure. As long as it's not 8.1, because that's where alpha batteries are at. So I want it to be less than 8.1, and we'll see how that comes important in a moment. Okay, so going through to solve this, it's going to be k is equal to then 8.1, take 7.89 on 0.25 by the square root of 10. And if I put that all into my calculator, what do I get? We wanted something less than 8.1, which means that we're going to round down, because we don't want to go too far, so we actually include 8.1. So we're going to round down to 2.65. So round down So we are less than 8.1. But that's not our confidence level. So now we need to go to our calculator. Remember, the confidence level is given by the area centered on the mean. So if I go here, I want to know the confidence or the percentage that exists between 2.65 and minus 2.65. And this is on the Z distribution where we've got a standard deviation of 1 and a mean of 0. Okay, which gives us 99.195% or 99.1% if we round down again. What's wrong about that? Why do we know that we've got the wrong answer? So 1.51 is the correct value because the mean sample mean is 7.98. And then if I come back to here, I can then change that to minus 1.51 and 1.51. And that gives me a confidence level of 86. And I'm going to round down again. So it's going to be 86.89% or 86.8%. Again, we round down. So 86.8% is our maximum confidence level, which will enable us to make a definite claim about the mean. Now, it is important in the exam and the test that you just mentioned that you're rounding down to ensure that it's less than 8.1, just as a communication thing. So make sure you do put that note there. Okay. To take into account the different costs of 2 brands of batteries, the running time per dollar is calculated. For example, a battery that costs 90 cents has a running time of 8.2 hours. We have a dollar point of 9.11 hours per dollar. The table below shows the running time and the dollar performance. So we're given another table. The dollar performance of budget batteries is normally distributed with a standard deviation of 0.278 hours. Construct a 95% confidence interval for the mean dollar performance of budget batteries. What do we need to construct a confidence interval that we don't have? What have they not told us? Yep. What type of mean? Sample mean. Do we have a sample? Yes, let's calculate the mean from the sample. Joanne, can you give me the sample mean once you've got it, please? So we're going to find X bar. .87, thank you. And now we need to find a 95% confidence interval based on 8.87. Danielle, can you give that to me once you've got it, please? So just bearing in mind some of the key things we're going to need to know is that the standard deviation is 0.278, the sample mean is 8.87, and the sample size is 10 because it's the same as the sample we had before. Okay. So 8.70 up to 9.01. Okay. Okay. The mean dollar performance of alpha batteries is 8.18 as shown on the number line. On the number line, draw the confidence interval that we've just found in part C. So it was 8.70 up to 9.04. So 8.70 is all the way there, and 9.04 is up to there. So my confidence interval goes between those two values. Notice now that mu A is well outside this confidence interval. And because it's outside, we can now conclude at the 95% confidence level. So when we give a conclusion, we give a conclusion at a particular confidence level. We don't just say absolutely budget batteries are better, because the mean may be outside this confidence interval. We may have not captured the mean, but we're 95% sure we have. So we can say at the 95% confidence level, and then that covers us. You see, that statement covers us to say, well, we know we're 95% sure we got the mean. We're not 100% sure, we're 95% sure, so we can make a claim at the 95% confidence level. The mean of budget batteries could be as low as $8.70 per hour, which is well above the dollar performance of alpha batteries. Hence, at 95% confidence, budget batteries are better. Okay. What is the maximum level of confidence which includes the mean of A? So mu of A is equal to 8.18, and we want the lower bound to equal 8.18. We want it included this time to ensure that we get that. So that means that x bar minus k sigma on root n has to equal 8.18 or be less than it, less than or equal to 8.18. Now, what was X bar, Joan? What was X bar again? I think that was our lower bound, isn't it? 8.87. Okay, so 8.87, take K, we're going to solve for K, times 0.278 on the square root of 10 has to be less than or equal to 8.18. That's going to ensure that we include the mean of A. Okay, so if I move this to the other side, I get negative K 0.278 and the square root of 10 is less than or equal to 8.18, take 8.87. And then I'm going to bring all this other stuff to the other side, so negative K is going to be less than or equal to 8.18, take 8.87 times by the square root of 10 on 0.278. And then to get rid of this negative, I need to divide it through by the other side. But what that will actually ensure is that the sign swaps around. So K has to be greater than or equal to the negative of that. And Ethan, can you give me that number, please? Now, you might think, well, that's odd. We said it needs to be less than this number, but now the sign swapped around. But remember, we're saying K is determined by the confidence interval, or determines the confidence interval. So if K is something or greater than that, we're going to get a wider confidence interval. And remember that a wider confidence interval includes more values. So if we're trying to go below this value, it's going to be at a certain point or wider. So K is going to be at this certain number or more, because that's going to mean a wider confidence interval. Okay, all right. 7.849. All right. So we can call that 7.85 because we can go greater than that. So here, I come back to this point. 7.85 on the Z distribution, going between that and negative, the negative of that. One. Why is it 1? Yep. Yes, that's right. So basically the question isn't a great question because it's too big for the calculator to handle. We can never have 100% confidence interval. Okay? So to 3 decimal places, it would be 99.9% confidence. We cannot have 100% confidence interval. Okay. That's about all we can do. The question isn't a great question more than anything else. They wouldn't give one where you get a number, final number of 1. Okay, all right.